Hello.
Yes, Naveen. Can we
Yes,
start?
sir. Can I start? Yes, I can start.
Yeah, please start.
Okay, fine. Good evening, guys. Welcome to our, I think it is fifth session. Yes. So, in the previous class, we have ended our class with discussing the problems of 2017 set 2 only of production and manufacturing, and we haven't completed the industrial part of it, right? So, though the title of this video says the production and manufacturing of 2018 paper, the first 15 minutes of, or 15 or 20 maybe, something around that minutes will be discussing the 2017 set 2 industrial engineering questions. Okay, so I should have clubbed in the previous class, but as we have 2 hour sessions, so we have stopped it. But yeah, we of for 2018 paper, the session starts after 15 minutes. The first 15 minutes will be discussing the industrial part of 2017. Okay, let's start. So this is the industrial 5 questions. The first question says statistical process control chart which shows the number of defects found in a subgroup of fixed size is. So yeah, we'll find the answer. Yeah, it is there. But as we have discussed in our previous sessions, we are going to discuss each and every option and discuss what is about the separate option. And then after discussing the options, then we'll read the question and then we'll come to the right option. Okay. So let's see what is C chart. C chart is also known as count chart. Okay. If you know, it's good. If you do not know, please follow. Is count chart. Right. So count chart is it's just some kind of a statistical analysis or a statistical tool which is used in quality control to monitor the number of defects in a process. Right. Monitors number of defects in a process. Okay. So the C, whatever you are seeing here, it stands for count. Okay. So it is used when the number of defects per item or maybe some kind of a group. That's what they have written here, subgroup, right? Right. Uh, if the number of defects are counted in that group, right, then that is what is count, right? You're counting it, right? So this chart will tell you the defect in that can occur in large, and it won't say the how rare the I mean there are two things, like these are all are probabilistic, right? So it will say the number, but it won't say how frequently it is going to occur in some groups, right? So for this question, A is the right answer. But yeah, but we'll be discussing what about the other charts as well, right? R chart, R stands for range chart. Okay, so it discuss about the variability of a process or how dispersed the process is. Okay, it's not about the count or defects. It's about the process itself. It's not about the defects, right? So it discusses about the variability of a process. It's all plots. If you go and type in Google, you'll get some plots, different plots. The process. Variability of how varying the process itself. It's not about the defects. See, defects will come after the parts have been manufactured. The process itself is because of so many variations, right? It can be anything, environment, the person who is working. So many things are there. So variability of process itself. The main thing is environment, like how you're trying to do the process. Control chart is where is the kind of a super group, or see, under control charts you get the C chart and R chart. Okay, let me write this. You have C chart and R chart, X chart. There are so many things. Okay, let's not discuss that. R chart. So C chart and R chart, I mean count chart and range chart are types of control charts. It's kind of a graphical representation of the process over time. Okay, so these are graphical representation of process over time. Good. And next is Gantt chart. So if you have attended our classes, or if you are attending our will be attending our classes, we'll be discussing, we have discussed or discussing the Gantt chart when we are doing this assignment problem. Assignment comes under linear programming problem in industrial and operations research syllabus of GATE. Okay, so when you're assigning something to a machine, right, then you see about what time the machining is happening for certain amount of products. See, I'll tell you an example. Here, let's say there are two machines, machine 1 and machine 2, let's say. And there are some products A, B, C, D, all these things have to be manufactured. And each product has to go to machine 1 first, and then after machine 1 only, it has to go to machine 2. Because maybe there is some kind of an operation that has to be done on machine 1 before doing it on machine 2. It's not the vice versa, in the sense like you cannot start with machine 2. You have to start only with machine 1. It's kind of a first step, right? So let's say A will take 2 minutes in machine 1 and 3 minutes machine 2, and B will take 1 minute on machine 1 and maybe 2 minutes on machine 2. Like that, there are, already there is some kind of a time that is being mentioned, right? Timing of each task has been mentioned. Now we'll be drawing some kind of a Gantt chart saying that, so this is machine 1 and this is machine 2, like this, and we'll have some this is product A and this is product B. We'll have something like this. Okay, so then product A will take 2 minutes, then immediately product then and then after product A 2 minutes only, then B will start, right? Sorry, on machine 2 3 minutes here. So this time when product A is doing its machining on machine 1, machine 2 is free. Like that, we'll be knowing some idle times and the sequence of timing, or maybe we can represent the timing of tasks arranged based on the machines and all, right? So this is used for quality and control purposes. Okay, so this chart is known as Gantt chart. Okay, fine. So I love this, but I'll just write what is this. It's nothing but the tool to or tool to represent timing of charts, timing of tasks, tool to represent timing of tasks, right? So hence, out of all the question, a statistical, let's read the question now. A statistical process control chart which shows the number of defects found in subgroup of a fixed size is. Answer is A. Okay, very good. Next. In the process chart, the symbol used for inspection is. Okay. So there are different symbols that are used when you are doing this inspection. So I'll write what is what. So this represents operation. Operation is happening, right? When the process is happening. And this represents inspection. Inspection. This represents transport, dispatch, transport. It's in transit, the items that you have manufactured, and this represents storage or inventory. Okay, so in the process chart, the symbol used for inspection. Inspection. So answer is B. That's it. And maybe there are some other symbols like there is some kind of D symbol that is for delay, right? And here, if this arrow, whatever you're seeing is filled, let's say, then it is rejection point. Then there are some symbols you have to remember. That's it. Okay, fine. Now, transportation method is concerned with, okay, so if you have done, if you if you have at least have seen the syllabus of gate in mechanical, then this answer is easy, because in linear programming problem they will mention transportation as subtopic. From there itself you can easily understand, okay, transportation will come under linear programming problem. So answer for this is a linear programming problem. Answer is B, but we'll discuss what is value analysis and what is linear programming, queuing theory and break-even analysis separately. So what is value analysis? See, best value analysis is like increasing the value of the service, increasing the value of the goods or service, value analysis, right? So improve value of goods or services, goods, products, whatever it is, services also, with reducing cost, with an aim of reducing cost. Okay. Linear programming in other ways is to optimize the things. That is very important. Optimization, the best outcome. But the in linear programming problem, there are three things that you have to have. The first one is objective function. First, you have an objective, right? Then that objective function should be a maximization problem or a minimization problem, something like that. And then it will have some constraints, because you cannot have infinite resources, infinite time. So there are some constraints on resources, right? So you have some constraints. And if you have these constraints and an objective function, you should be able to minimize or maximize the objective function based on the constraints. And that is what is your linear programming problem. Why it is linear? Because your objective function, your constraints, everything is linear in nature, in the sense the equations will have of degree 1. Okay, so this is for kind of an optimization problem. So transportation is also some kind of an optimization problem, because let's say you have some kind of if you read the transportation, it will be easy for me, easy, right? You have some kind of demand and supply thing, right? So you the this is demand and this is supply. Okay, so now let's say there are 80 cars that you have to send to some place, and 30 cars you are manufacturing in. Okay, the demand. Okay, so I'll tell you there are some places like Delhi, maybe Kanpur. They are North Indian side states I'm wanting putting. Okay, Kanpur, maybe Patna, and Kolkata. Right, there are some places where there is a car manufacturing plant, and 80 cars are being manufactured by Delhi. 30 cars are being manufactured by Kanpur, and some 50 cars are being manufactured by Patna, and some 70 cars are being manufactured by Kolkata, let's say. And the supply points or South Indian points, let's say Hyderabad, Bangalore, Chennai, and Kochi. So Hyderabad requires some number of items, Bangalore requires some number of items, Kochi will require all this will happen. So now which item has to go from where to where? Delhi can give items to Hyderabad, items to Bombay, items to Chennai, items to Kochi also. But how many? It will be based on how much is the transportation cost, because reaching from Delhi to Hyderabad will be of different cost, reaching from Kanpur to Hyderabad will be of different cost. Like that, there is some kind of an objective here to minimize the cost. What is the objective? Minimize the transportation cost. What are the constraints? The route, which route you have to go, and the demand and supply is the constraint. So through this, you'll be able to solve this optimization problem and get to an optimal point or optimal route where you minimize the total transportation cost. So this is the LPPR are having so many things like one is transportation is one method, and assignment is also kind of a linear programming problem, right? And on the other hand, queuing theory will involve some kind of weighting principle, right? When we have to weight something, so it's a simple queue thing, where if you want to get some service, you'll stand in some kind of a queue to get to get the service, right? So it affects the service oriented industries mostly, right? So let's say if you're going and standing for something for service, so you should not get tired, or you should not get because human is having this kind of things where the patience level is very high in some cases and very low in some cases, that might affect the business of certain persons. Okay, so it's primarily the balance between the demand of that service and the resources that the consumer can provide. Okay, so this involves waiting, something like that. So it right, 1 minute. Yeah, so it is like balance between resources and demand. So this is not the answer. And break-even analysis, you might have known already this thing. It's nothing but what is the amount that you have spent for some kind of service, well, for some kind of service, how much service you got, right? So how much revenue you have spent and how much you got, right? So it's a tool to analyze whether you have reached break. They say no, whether you have reached break in analysis. Let's say if you have invested some money in some kind of a business, right? So let's say you have invested some 50 lakhs rupees in the business, and then you over the period of time you are getting the returns, and after some time, whatever you have invested, you got them. Then when you have invested 50 lakhs and you got 50 lakhs, then you say you have reached your break even. Then after a certain point, whatever you're getting is profit, right? So this lets us know the profit or loss, or maybe both. Okay, good. Adaptive response rate forecasting is related to what? Okay, so production planning. So we'll discuss the option first, and then we'll go what is the right option. Production planning. It's like it's a very broader term, right? It's a planning of a production in aggregate level, right? You'll read, no, we'll read about AGP, MRP, right? Aggregate production planning, material market resource MRP, material resource planning. Like that, we have so many plannings, right? So mostly we have this aggregate production planning, right? Aggregate AGP, right? Where we discuss something about decisions to make to manufacture the products and when to produce. All these things will come, but it doesn't require any forecasting analysis, right? And adaptive means like changing. Adaptive is nothing but change in time. Adaptive means like today I'm going to run for 1 kilometer because I am not feeling good. Maybe tomorrow I'm going to run for 2 kilometers. But I'm going, because I'm full energetic. I've taken good food. So it will adaptive based on the situation. You'll move. That is called adaptiveness. Adaptive to the situation. So the adaptive response forecasting is nothing but change of forecasting value based on the time, based on the situation also. So production planning will not have any forecasting or something adaptive rate forecasting. Okay. Production schedule also is something like that where you don't have any forecasting thing. It's a simple scheduling that you're making, like what is the machine availability, how many shifts in a day, 3 shifts are there, how many people have to work in a shift, right? What are the maintenance activities that you're planning, right? All these things will come under production scheduling. Okay. So this is about machine availability, right? Maybe maintenance activities, and etc. etc. It doesn't have any for adaptive response forecasting, rate forecasting, right? Value analysis already we have discussed. It's to get the good value for minimum cost. Good value for minimum cost, or for minimum cost. This we have discussed in the previous question, right? So it doesn't have any rate of. The only where it will come is inventory control, because so what is inventory? Inventory is like you put some kind of products at your garage or at your warehouse for the unforeseen demand. In the sense, like you get a lump of amount and put it in your place so that you can use that in the later stages. Even though you spend so much amount of money, but that will be able to justify if you're using it, using the resources that you have bought at right time and right place, right? See, you because how much to bring is very important. So how much inventory you have to keep. That inventory will be kept based on the actual rate of demand, right? So what will be the demand? We don't know, but the demand will be forecasted, right? So let me say the example. Let's say I thought that I got some 10 kg atta, the wheat packet in my home, assuming that it will last for some 10 to 15 days. But suddenly, relatives have come. It has been completed in 5 days, or maybe suddenly you went to your relative's home and your atta has extended till to 30 days. So initially, before buying it, you had a thought that it will last for 15 days. That is what is forecasting, right? So you forecasted the demand value, then based on that value only you have bought the inventory for your home, right? The same way, adaptive response rate forecasting is related to inventory control, not the value analysis, not the production scheduling, not the production planning. Good. Okay. Next. Frederick W. Taylor introduced a system of working known as. Actually, the answer is functional organization, but we'll discuss what is line organization. There is nothing something like effective organization. I don't know it. Effectiveness means like it is very effective, but line organization is very important, where you have chain of command. Chain of command is very important in the line organization. Like military people, you have a chain of command, right? Chain of command. You have your superior, and superior is having some other superior. Like that, you have so many commands, right? Based on that superiority, you'll be having the problem solved. Let's say you have some problem you couldn't solve, even to your superior. Your superior also has failed to solve that. Then your superior will know your his superior, his or her superior. Like that, this is like kind of a line organization system where the it's a clear cut chain where it goes in a lies. But the problem only will come only when if there is a person missing or there is any some kind of and it is completely depending upon one to other. You can't go and directly talk to your higher level authority. You have to pass through the chain, because that will impede the progress. That is the disadvantage of line organization. The other way, the functional organization is where you group your the departments, right? Groups or departments or departments. Right? So let's say one group is there, and that group are specialized in turning operation. Now let's say you have a problem. Directly you can go to that group and you can ask. No need of any chain command. Directly it's like functional, right? Different in like now line organization is not there in companies. It's all functional only. Let's say if you're going to some engineering college, you have some departments, right? Organization. All the mechanical people will sit in mechanical department, right? If somebody is having some problem, they'll go to mechanical. The same way in a specific company, you have some engineering department, marketing, sales, finance, right? There are so many departments. Based on that thing, you'll be able to go and take the help, and interconnectivity also will be there. So this system is introduced by Frederick W. Taylor. Okay. How do I know his name? Yeah, you have to remember that is the question they have asked in the examination. Good. So that is the end for the 2017 part set to 2 industrial engineering paper. Now let's go and discuss the manufacturing part of 2018 paper, and this is where our actual uh, class starts from, because the title of our video says 2018, but the first half an hour we have discussed the 2017 itself. But from here we are starting 2018 mechanical engineering, that too for manufacturing and production. Okay, good. So there are some 14 questions around. We'll be discussing one by one. The first question is the frequency of ultrasonic waves is. Okay. So first you have to know how many. What is frequency? What is frequency? See, in a wave, in a sound is form of a wave. You know that sound is form of a wave, right? Okay. Here they're not talking about any sound. They're talking about wave. Okay, wave, something like this, right? So the difference between the crest and trough. So this is crest, trough. The difference between is amplitude. And how many are happening is here the amplitudes in time is frequency. How many peaks are coming in frequency? So this is having less frequency compared to this is having more frequency, more waves in a single time, more frequency. The pitch the same, more pitches. Okay. So this is again amplitude, right? So they're asking in the frequency of ultra. So they're asking the frequency. How many ups and downs? How many wave? How many ups and downs? How many crests and troughs are there in a single time? That is what is hertz by time, right? So generally, if you see the range varies from 20,000 hertz to 20 hertz. Why I'm writing here like this? Because this range is your audible range, audible where you can listen. A human ear can listen, and here it's called ultrasound, where you cannot hear, ultrasonic or ultrasound, and here it is infrasonic or infrasound. The frequency is increasing in this direction. Right? So hence ultrasonic are having above 2000 hertz, right? So above 2000 hertz is the answer. That's it, right? Infrasonic. Okay, I wrote sound. Sound also they'll write infrasonic. You can say if you want. Okay, good. Loudness of sound doesn't change with the change in. Okay, so first, what is loudness? Loudness will depend upon the amplitude of your wave, sound wave. Depends on amplitude of sound wave. It doesn't amplitude in the sense like this. This is one wave. This is another wave, right? So this is louder, more loud. Okay? So obviously loudness will depend upon amplitude, but they're asking doesn't change. So obviously loudness will change with distance from source of sound. Okay, if you are here and you are shouting here, so as you keep on you are shouting here, as you keep on going, the intensity of sound will be reduced, or sometimes it will get dissipated as we distance is keeping on increasing. So obviously the loudness will depend upon amplitude, and loudness will depend upon the distance between the source and the sound person, the person who is listening and the person who is making the sound, right? So it doesn't depend upon the frequency. Okay, frequency is like number of sound waves or number of waves at a fixed point for a given period of time, right? So frequency is the answer. Good. Next one. A whole of dimension 60 plus 15 and 60 minus 0, and the corresponding shaft is of dimension. Okay, so let's make the dimensions. So let's take this. This is your okay. I'll fill it with, sorry. I'll fill it with something like this. Okay, good. Okay, now this, oh, what happened? Okay, so this is whole. Sorry, whatever I'm showing is whole object, and the tolerance of whole is here. Okay, and the top, this is shaft. Okay, I'll show you the shaft also. Okay, let's make the different diagram. This is not making sense. Let's make only 1D diagram, so it will be making some sense. Otherwise, you'll be getting confused. So baseline, we'll make the baseline first. Zero line. What is zero line? This is 60. Very good. That is what is given. 60 is 60 only, right? The original dimension should have been 60. And they're saying the dimension of whole is this much. In the sense, you have 60 plus. So whole will go in the opposite direction, right? So the minimum is 60 itself and a maximum is this much. So the tolerance is this much. Tolerance of whole is this much. Whole, and this is 60 itself, and this is 60.015. It is the whole tolerance, right? And for the shaft tolerance, what are they saying? 60 plus 0.011, and the sense like they're talking about here, that is 60.0, 60 point this much. Oh, it is some this much, and the minimum is 60 minus, so here it is something like this. Okay, this is for shaft. Okay, let's remove this 60 here, not to get confused. And this is this, and here this is 60.01, sorry, 011, right? So what is 60 minus 0.001, right? It is some 599. Okay, so it is 59.999. This is for the shaft. So if you see, there is some kind of an interference between, right? So clearance fit is when this is clearance fit. The clearance fit, now the diagram looks like something like this. This is clearance fit, right? Interference fit is like hole will be at bottom and shaft will be at top. So, and for transition, this is what will happen, both in between, like this, right? This is hole, shaft, hole, shaft, hole, shaft, and this corresponds to this. Answer is transition shaft fit, right? So in interference fit, you take any dimension of hole or any dimension of shaft, it will not fit. In clearance fit, you take any dimension of hole, any dimension of shaft, it will fit every time. In transition fit, you take the minimal, you take the maximum hole size and the minimal shaft size, then it will fit, something like that. Okay. Here, see, if you take the 60.015 and 60.011 combination, it will fit. If you take 60 and 60.011, it will not fit. So that is called transition fit. Okay, good. Next, which of the following carbon steel is most weldable? Okay, so generally they are having some carbon. So why carbon is added? That is important. So weldability is the capacity of some kind of a metal to be welded properly without any uh, cracking or distortion or some kind of like that, right? So should not have cracks or some distortion. Distortion will happen because of the temperature gradients. Cracks will happen because of the brittleness, right? So what does carbon do? Carbon will try to increase the brittleness in the steel, right? So first carbon percentage increases, it will increase brittleness. If brittleness increases, what happened? There is a chances of cracks. Chances of cracks. Because of that, more carbon, more chance of cracks. So those are not weldable, right? So therefore, in the given options, you can see 0.15 is the zero or less carbon that is available. So as it is having less amount of carbon, it means that low carbon content. It means that low brittleness, right? High amount of ductility, and hence you don't have any crack tendency, and that is called weldable material, right? The weldability will be good in the low carbon steel, that is 0.01, 0.15%. In these options, low carbon means 0.008, also low carbon only. But here, according to this given options, compared to all A, B, C, D options, 0.15 is less. That's why I'm taking this answer. Okay, good. Small percentage of boron is added to steel in order to, yesterday we have discussed boronizing, all these things are adding the boron content, right? So if you increase the boron, yesterday also we have seen, again and again I'm saying, if you increase or if you have small percentage of boron in the steel, what happens? It increases hardenability. It increases hardenability. Answer is D. We'll discuss other things. We'll discuss who will increase endurance strength, who will increase the wear resistance. All this we'll discuss. First, we'll discuss about the boron. So how much percentage of boron is added? Some 0.0012, some 0.003, small amount of percent of boron is added into the steel to increase the hardenability, right? So how does it increases? Because it refines the grain size of the iron atoms, the steel, and it enhances the alloying effects. So by this is again I'll write, increases the hardenability by refining the grain size of steel, right? And what about others? Who will increase the endurance strength? Generally, if you add some amount of nickel, right? If you have had some amount of nickel and maybe chromium or maybe molybdenum, right? All these things, all these materials are all alloys, not materials. All these alloys are added into the steel to make the steel increase its endurance strength. Endurance is like for cyclic loading. You might have read this thing in your strength of materials of machine design, right? So actually, nobody wants to reduce the machinability. Everybody wants to improve the machinability, right? So lead is an item to increase machinability. Machinability, not reduce, increase. Who will? We have discussed this yesterday. Who will increase this wear resistance? Chromium. Answer is chromium. If you have chromium, it will have wear resistance. Okay. So answer is D. That is increasing the hardenability. Number of atoms of a face-centered cubic lattice. We have discussed in our 2015 and 16 paper also. Same questions. This question has been repeated, and the options are all simply easily we can put here. So we'll discuss the simple cubic, BCC and FCC. This is what is simple cubic. We have seen, right? Simple cubic, and this is your body-centered cubic. Body-centered cubic. This is face-centered cubic. So if you see why it is a simple cubic, because all the atoms 1, 2, 3, 4, 5, 6, 7, 8, right? All are sharing. It's taking 1/8 of each. 1/8 of atom is coming in. So this is 1/8, right? So what is the effective atoms? Effective. They're asking effective, right? They're asking the number of atoms, effective atoms. So effective atoms, effective number of atoms for simple cubic is 1/8 into 8 corners will give you 1. So the effective atoms are 1 in this case. Here how much? This is 1/8 and there is 1 full. So here I can say the effective atoms are 1/8 into 8 plus 1 will give you 2. Right, here also you can see face-centered cubic. Here it is 1/8 and this is 1/2. And 1/2, how many faces are there? 6 faces are there. How many corners are there? What is this corners are there? 1/8. So here I can say 1/8 into 8 plus 1/2 into 6 faces. That will give you 1 plus 3, that is 4. So in face-centered cubic it is 4 FCC. Right? That is the answer. 4. Simple. Okay. Next. Which of the following order of crystal structure will match with metals iron, nickel, titanium in that order at room temperature? Okay. So here we have to remember the list. There is no other option. So I'll write the list first, then we'll discuss, right? So here BCC structure we have seen, body centered cubic we have discussed. That is, it has having some atom at the center, one center, and at each corners there is one atom which is contributing one eighth of its portion, and hence the effective number of atoms are two here. We discussed, right? The same way BCC. So the examples of BCC are having structures which are having BCC are iron at room temperature, right? And chromium. Chromium is also at BCC structure. Tungsten is also a BCC structure, and etc. etc. I can search for so many materials. FCC is sphere centered cubic. Again, we'll have aluminium Al, right? Copper Cu, silver Ag, right? Au, sorry, Au or Ag. I write silver. I don't remember gold and silver. I confuse every time. I'll write silver, right? So, can you identify this one good thing? You can see these are very softer. FCC atoms, no, very softer in nature. Aluminium, copper, gold, silver, all these things are softer in nature. So, if you see a softer material, then assume that it is mostly FCC. Very common materials I'm saying. Okay, and HCP are having some kind of zinc, magnesium, right? Maybe HCP is not hexagonal closed packing. Okay, hexagonal closed packing. Okay. So how the structure will look like? You have 6 atoms like this, and here also you have the 6 atoms. In between you have 3 more atoms like this. These are hexagonally closed packing atoms. Okay, so magnesium and titanium. Titanium is also one of the options. Titanium. Okay. So what is the question? Which one of the following crystal will match the metals? Iron, BCC. So iron is BCC. Nickel is, I think it is. Where did I write nickel? I didn't write nickel here. Huh? Okay, nickel is very softer, so I can write it is FCC, no problem. And titanium, obviously we have written, so this is we write nickel also here. Yeah. Titanium, obviously we have written it is HCP. Right? BCC, FCC, HCP, and this is the answer. Okay, good. In a machining operation, cutting speed is reduced to 50%, reduced by 50%, assuming n is equal to 0.5, c is equal to 300 in Taylor's two-life equation, increase in cutting tool life. It's a simple question. Already we have done this question in the previous year papers also. It is given by Taylor's two-life equation. Taylor's equation. What is Taylor's two-life equation? V t power n is equal to constant. V t power n is equal to constant. C is given, n is given, and they are saying two conditions: cutting speed reduced by 50. So in case one, something V1, cutting speed has been reduced by 50%, in the sense 0.5% of V1, and they're asking what is T2, increase in two life. What is T2? Or maybe T2 by T1, something like that they're asking. Or maybe they're asking what is the value. Okay, let me take this thing. So maybe they're asking some x into T1, and what is this value of x? Something like that. Okay. So let's do this thing. So we can use this V1 T1 power n is equal to V2 T2 power n. Right? So there is no need of C here, they have given, but n is important, that is 0.5. So V1 T1 power n, that is 0.5, is equal to 0.5 V1 into T2 power 0.5. So V1 gets cancelled, right? T1 or T2 by T1, T2 by T1 is equal to 1 by 0.5. 1 by 0.5 is 2. And please do not forget this 0.5, this is 1 by 2. So T2 is equal to 2 power 2 into T1, that is 4T1, right? And hence it increases by 4 times. That's it. And this X is 4 here. Finished. Okay, very simple question. 1 minute, less than 1 minute you can do if you are very fast in calculation. Okay. In a linear arc welding process, the heat input per unit length is inversely proportional to. Okay. What is heat input? We'll write it. Heat input is I square or V into I. V into I. Heat input. They're asking inversely proportional. Here, see what is V? V is welding voltage. I is welding current. Both are directly proportional. No? So this and this is not right answer. As what is duty cycle? Duty cycle is nothing but D is equal to time on divided by time on plus time off. What is this time? The time of which the welding is on, and after some time it will be off. It's a pulsed on and off. This T on, this is T off. For some time it is off. It is no way related with the heat input, and it is, we cannot say whether it is inversely proportional or we cannot say. So obviously this is not right. The only answer is welding speed, and yes, it is true. Why? Because heat input in terms of welding speed can be given with a formula as V into I into some efficiency, right? Okay, this is not heat input. This is heat input. Oh, okay. So fine. Let's not do heat here. We'll put it here itself. Okay. Square R. This is time t. So let me divide with some time t. So this is t here. Okay. This is important for time. Okay. So why it is building speed? I'll tell you. Let's say you are going in this direction, you are depositing in this direction, and you're going like this, right? If you're not spending, if your welding speed is very high, very fast, you're not spending much time at that location. As you're not spending much that time at that location, the heat input that will be less. So if your welding speed is very high, heat input will reduce. Welding speed is less, heat input will increase. Hence welding speed and heat input will be inversely proportional to each other. Okay, good. Good. Welding process which uses a blanket of fusible granular flux is. So there are some options, but we'll discuss each one of it. I've put the figures readily. One is submerged arc welding. What is the submerged arc welding? The submerged arc welding is nothing but a weld metal, and you have, can you see here? This is what, okay, I'll put it the laser powder. So this is some kind of a flux, powdered flux that is placed before itself, and the arc is submerged inside this flux, right? So arc is already submerged inside the flux, you cannot see the arc. That's why it's called submerged arc welding. See, this arc is submerged inside the flux, and as you proceed, the flux is keeping on coming. As you proceed in the right side direction, this is the already welded part. And this submerged arc welding is used for joining pipes and ship hulls. Big heavy equipment can be, heavy thickness plates can be joined using this submerged arc welding. And the other one here, what you see on the right hand side is the TIG welding, tungsten inert gas welding. So what, and here this is the electroslag welding, electroslag welding, and this is thermite welding. We'll discuss one of all of it, not one of it. Okay. So you see tungsten inert gas welding, there is some kind of a tungsten electrode where you try to put the arc, and there is a filler material that is coming separately, and there is some gas, inert gas that is flowing through. That inert gas is flowing through here, and as this is heating, there is some kind of another place where some liquid cooling also is happening. Liquid also is being passed. This is costly, but yet this is having good properties of welding. Okay, this is tungsten inert gas. Tungsten is the electrode material. Inert gas is passing through to protect the environment, to protect the weld pool from the environment. Okay, and here we have electroslag welding. That is, you see, if you hear, it's kind of a, this is a water out, water in, and this is a shoe. They call the red color one is a kind of a shoe, and these are the two plates. Green color ones are the plates to be joined. So this is going vertically upwards, you see, and this shoe, red color one is shoe. It's called shoe. Okay, so the red color one will keep on moving up as you proceed, as you keep on depositing in the vertical direction. You keep on move, go up, go up, go up. The shoe will be protect to not to spill that weld pool outside. That's it. This is called molten slag. So this is called electroslag welding. Okay. And what is thermite welding? Thermite welding is kind of a casting only, where this will be used in the locations where you do not have access to electricity, because here we need electricity, here we need electricity, here also we need electricity. In these first three we have to have electricity access. Until unless that, we cannot do this operation. But here electroslag welding, sorry, thermite welding, there is no need of electricity. So in some kind of hilly areas or very remote locations, where there is a very scarcity of electricity, you can use this kind of welding to join. So if you see, this is some kind of a train tracks, railway tracks are on 5 section beams, right? So those can be train railway tracks can be joined by using this thermite welding. You would have seen there is some kind of a machine will keep on moving as railway track is being built, right? So what is that? You have a thermite mixture. The thermite mixture is nothing but 8 parts of aluminum and iron hydroxide. So when ferrite hydroxide. So you put this thing and you have this conversion, and that will give you so much amount of energy. That is 3310 kilojoule per mole of heat, and that heat is used to melt the material here. So this is thermal mixture. There is a material that you put, you ignite it with some kind of catalyst, and when you ignite it, it will immediately rise the temperature in minimal of time, and the material that is there here will be getting melted very fast, and then it will get to pour into this, and then you join the sections. It is some kind of a casting only, but you're trying to pour in between two railway track sections to join them. Okay, so this is called thermal welding. Now let's see the question. What is the answer? The welding process which uses blanket of fusible granular flux. Now it is very simple to answer, right? It is submerged arc welding. That's it. Very simple. Okay. Now next. In a sheet metal of 3 mm thickness of hole, 7 mm diameter needs to be punched. So let's do that. So sheet thickness is very low, and hole, right? Okay. So if you see the hole will be like this, right? This is how much thickness? Same thickness. Thickness is 3 mm, and the diameter is 7 mm. Right? Now you're punching it, isn't it? You are punching to make the hole. The yield strength and tension of sheet metal is 120 kilopascal, right? So yield sigma y is 120 kilopascal. Ultimate shear strength is tau, that is 100 megapascal. the force required to punch the hole. Okay, what is force? Force is nothing but shear strength into area, area of shear, AS. Strength into area of shear. This AS is area of uh, shear. So the area of shear, I'll try to put it like this. So this is the area of shear around it. So this is the area of shear inside. Inside you have area of shear like this. This is area of shear, AS. Right. So what is that area of shear? It's nothing but area of shear is equal to, it is 2 pi r. Okay, it is given in diameter, right? So it is pi d. Pi d is the circumference of circle into thickness t. Into thickness t. This is thickness t, and this is diameter d. I'll write small d. Pi d is circumference, and thickness t will give you the red color surface area. And now d is given, t is given, tau also is given. You have to find the f. Right? So f is equal to tau into as, that is tau into pi d t. What is the value of tau? Tau is 100 megapascal, right? Into pi into d is 7 mm. 7 mm into thickness is 3 mm. Into 10 to the power of, okay, here I'll just convert into these things. So they're asking it in kilo Newton, right? So megapascal is given, right? So, okay, let me write that megapascal here itself. Let me convert that into pascals, 10 to the power of 6. 10 to the power of, okay, they're asking in kilonewtons, right? Okay, let it be 10 to the power of 6 pascals into pi into d is 7, right? 7 into 10 to the power of minus 3 meters Newton meter, right? Pascal in 2 meters square will give you newtons. Okay, fine. So 7 into 10 to the power of minus 3 into 3 into 10 to the power of minus 3. So this will cancel. It is something on 3 point. How much is this? Let's calculate. It is 100 into 3.14 into 7 into 3. That is 6.6594 newtons. That is 6 point approximately 6 kilo newtons. Okay, and that is the answer. That is 6. Okay, very good. Now, profile of a gear tooth can be checked by. Okay, so we'll discuss what is sine bar, bench micrometer, optical pyrometer, and then optical projector. Then we'll come back to the question. Okay. Okay, these are the sine bar, bench micrometer. This is bench micrometer. Bench micrometer, and this is what is optical pyrometer. And this is optical projector. Okay, so if you see the sine bar is used, simply you use sine rule to identify whether identify the angle of the component. So if you see how inclined the component is, you can easily find out how inclined the component is. What is the angle between the component if whether the plate is at an incline or whether the plate is at parallel to the surface. By using the slip gauges, by finding out this height, because you put the slip gauges, height is known, and the length of sign bar is already this L. So this height is known by slip gauges. Already L length is already there with the sign bar length, and then you can find this theta. Okay, and bench micrometer is again a linear dimension thing. It's a simple. Why it is called bench micrometer? Because you are putting it on. It's we are mounting the micrometer on a bench. That's why it's called bench micrometer. And of course, this is used for some simple measuring some simple dimensions. Okay, an optical pyrometer, right? Optical pyrometer is used for measuring the temperature of an object or temperature of a surface. Temper Temperature of a object or surface. Right? How you have this hot body here, and then there is some kind of a lens, and then you have a bulb here. So you see from this place, and you adjust your rheostat to increase the radiation intensity of radiation. You by controlling this whatever it is, you increase the temperature of this filament bulb. As you increase that, there is some kind of a radiation energy that is going and falling onto this lens, and already due to this heat body, there is some kind of radiation that is happening on this lens. Both the intensity patterns have to be matched. And how do you know it is matched? Because you are looking from here, you see the patterns. If they are matching, and you are seeing this through this filter, right? If they are matching through that filter, and then from that you can be easily able to find out, so how much input you are giving. From there you can easily find out the temperature of that body. Okay, so that is how it's on comparison of intensity of radiation, right? So through that we'll be able to match the intensity of the reference filament that you can see here, and the object of consideration, that is your hot body. So that is what is optical pyrometer is doing for measuring the temperature of the surface. And the next one is the optical projector, where you see here you have a light source, you have a colorimeter lens, and this is the object. And as it is going and it is projected, you are magnifying it, right? So either this is a here you'll get the magnified image, right? And based on that you'll be able to identify the profiles, because you got the magnified image, right? You can find out the profile, so you can easily visually see and detect the profiles. So hence you come back and see the question, what is the answer? Profile of gear tooth can be measured. Sign bar, no. Benchmarkometer, no. Optical parameter is temperature. So the only option that is relevant is optical projector, through which you can easily test the profile of gear tooth. Okay. Next, the reflector combined with autocollimator can be used for checking. What is autocollimator? First, we'll see. This is the autocollimator. How does also autocollimator will work? We'll discuss. Okay. So if you see here, you have the light source. The light will come here, and it will take a 90-degree turn here. It will go through the collimating lens, and it will hit the ray. Again it will come back. If it is not inclined, if it is okay, this, so if it is, let's say if whatever this is inclined, right? Let's say if it is like this, straight, it's not having any inclination. So then when your light is coming here, it is coming here, it is coming here, again it will reflect back straight line like this, and there is no distance of x, no distance. If it is not inclined, let's say if there is an inclination, obviously you go like this, and it will deflect, and it will come like this. Right? So you can easily see the deflection. You can easily see the deflection, whatever the eye here, through the micrometer here. There's a micrometer. Through that micrometer, you can see the deflection change. Based on the deflection, you can calculate what is the angle here. right? So this is what is deflection, and this is what is the focal distance f. What is the focal distance f, and what is x, and what is the deflection, right? Based on that, you will easily find out what is the theta. So we have the formula that is x is equal to 2f theta, where x is the distance at eyepiece, and f is the focal length, and t is the angle of tilt. If you know this, and you can calculate the theta of inclination. That is what is called autocollimator. Okay, now let's go and see what is the question. The reflector combined with autocollimator can be used. So this is the collimatic lens, and this is the reflector, and all these things are happening. So obviously it is used for parallelism. No, of course it's not used for parallelism. Parallelism can be found out by only autocollimator. You don't have any reflections, right? So this is not the answer. Circularity can be found out by some kind of coordinate measuring machines, cylindricity, sphericity, all these things by CMM machines. Autocollimator will not be used. Surface roughness machine also autocollimator will not be used. It is like some profilometers, surface profilometers will be used. Surface profilometers will be used. So autocollimators will not be used. Alignment, yes. So here you can see the theta, how much is that? Then you can adjust here. Based on that, the distance will be reduced. Based on that, you can easily align how much is the tilt. Based on that, x will change, and you reduce the theta, x also will be reduced, because the x and theta are directly proportional to each other, right? Good. So answer will be alignment. Okay. Good. Which of the following is amorphous material? Okay. So first, what is crystalline and amorphous? Crystalline material are regular fashioned. Amorphous material are not regular fashioned. Regularly arranged. Not regularly arranged. The atoms are not regularly arranged. Regularly arranged. Okay. Crystalline is opposite to the amorphous material. So let's go to option by option. Mica, it's a very good mineral that is available in the form of layered sheets. Layered sheets. So obviously this is crystalline in nature. What is crystalline? Regularly arranged. Right? Lead is another element which is crystalline at atomic level. Right? Crystalline. Rubber is an amorphous material, but natural rubber is partially crystalline. Right? The crystallinity of rubber will be increased by a process called vulcanization. Vulcanization is a process to increase the crystallinity in the rubber. It is vulcanization is a process is the process where used to make the rubber. Okay, so obviously it is like partially crystalline. Right. So hence the answer is glass. Glass is amorphous, right? Because you do not have a regular or repeated patterns, right? So hence glass is amorphous. Amorphous, disordered or disordered atomic structure. I can write like that. Okay, good. Next. Okay, that's it. That's the end of the session for today. We have solved all the questions. So this is a very quick session that we have done for today, because we have started with because all the questions were very theoretical in nature. That's the reason why we have completed a little earlier than expected. So if you have any questions, please do comment in the comment section. I'll be able to identify them and answer them accordingly. So please remember, the first session, but the first part is of today's is from 2017 paper, and after half an hour of our session, then we have started the 2018 part of our ISRO question and answer session. Okay. Hope you took some knowledge from this class. Thank you for listening to this lecture or viewing this in the video recording. And let's meet in the next session. Thank you.